Hello everyone. Today we will continue the counting principles and then turn to the next section, the permutations. So first, let's study the subtraction principle. Let A be a subset of U. Let AC be the subset of U. Get rid of the element of A. You can write as X in U, defined by X in U, such that X not in A. Be the complement of A in U. So the principle says then the cardinality of A equals the cardinality of U minus the cardinality of AC. Just a small remark. In your textbook, they use A bar instead of AC. But later on, if you learn mathematical analysis or you have already learned it, then A bar usually we mean the closure of some topological set. So there might be some confusion. Although in discrete world, there should be no ambiguity, but I would prefer use AC. In topology, you usually use AC. Okay. Let's look at one example. So example 1. So computer passwords are to consist of a string of 6 symbols taken from the digits 0, 1, 2 up to 9 and the lowercase letters A, B, C all the way up to Z. Then the question is how many computer passwords have repeated symbols. Solution. So first, let's introduce some notation and do some setup. Let U be the set of all passwords according to the problem, and let AC be the set of computer passwords with no repeated symbols. Then it's easy to see by the multiplication principle, we can derive that the cardinality of U is 36 to 6. This is because you have 10 numbers and 26 letters. Okay, 6 is for the positions. You have 6 symbols. And then what is the cardinality of the set AC? Then you have 6 positions. First position, you have 36 choices, and then for the next one you have 35, 34, 33, 32, 31. Okay, then by the subtraction principle, the passwords with repeated symbols, the number of passwords with repeated symbols equals the cardinality of U minus the cardinality of AC. Okay. Here I would like to make another remark. The complement of A is A itself. Here actually we use this. Okay, next we introduce a division principle. So what is division principle? Given a finite set U and partition U into subsets with equal cardinality, then the number of subsets or such subsets of U equals cardinality of U minus divided by the cardinality of each subset. And now let's look at one example. So suppose K is bigger than 3 and less than or equal to n, and make a K pearl necklace from n distinct pearls. So how many necklaces are possible? So here refers to define what is same and what is a different necklace. So two necklaces are the same if they differ by rotation or reflection. For example, so let's make a remark. For example, if you have the necklace red one, blue one, green one, it should be the same as red one, green one, blue one, because you can flip it or reflect along the y-axis of the plane. Okay, just like for the necklace, you can wear it in this way or the reverse way. also, this is by reflection, identified by reflection. And there's another type of identification. This is by rotation. So suppose we still have the three pearl necklace. Now we rotate it around 120 degrees. Okay, so the red position becomes a position of blue pearl, and the green, the position for the green pearl becomes a position for the red one. And you cannot tell what is the difference between these two. So that's why we view them as the same. And in some fancy language, that is, you identify to necklaces by dihedral group. So dihedral group is generated by reflections and the rotations in the plane, and with the order 2K. Order is 2K. G. So this is a fancy language. In the fancy language, you can state it in this way. Okay. But for our solution, probably we can just do it manually. So solution. Suppose you have a string A1 to AK. So each one is a color. Okay. So let S be the set of the pearls. So first pearl, second pearl, to nth pearl. Okay, and let the string A1 to AK a string such that A1 to AK are elements of S. That means you take each position, you just put in some pearl, and also A1, AK are distinct. Okay. Then you consider the following map. That reveals the procedure how to construct a necklace. You have a string, and then you wear that up, A1, A2, all the way to AK, so that you have a necklace. So for example, let's see, suppose you have the following string of pearls. Okay. Then enter the map. You can name this as a necklace map or whatever. Then what do you have? First, you have the red one, and then you have the green one, you have the blue one, and you have the not this color, the purple one, and then connect these 4 pearls as a circle. Okay, then we want to use the division principle, we can set up as following. So first, step 1, let U be the set of all such strings A1, AK in S, A1, AK are distinct. Okay, and then it's easy to see the cardinality of U is n times m minus 1 times all the way up to m minus k plus 1. So the trick here is how to determine this number. You just noted that A1 corresponds to n, A2 corresponds to n minus 1. So the sum of the indices 1 plus n is n plus 1. 2 plus n minus 1 is n plus 1. So here k plus something should also be n plus 1. Therefore, this is n minus k plus 1. So that's how I determine the last term. Sometimes it may give you some confusion. What is the last term, especially when you have k plus 1, or several different numbers. Okay, this is a quicker way at least to check if you get the right answer. Okay, next, by the division principle, we should divide the whole set U into small pieces. Okay, so how to do this? Okay, so we do the following. Let T be the set of K pearl necklaces. Therefore, we need to get a number of the cardinality of T. And for each L in T, each necklace, let UL be the strings such that and the necklace map you get L. And then it is clear that if L prime are 2 elements in T, then cardinality of UL is the same as cardinality of UL prime. Then by division principle, cardinality of T is the cardinality of U divided by the cardinality of UL. Okay, then what is the cardinality of UL? Then we need to find correspond to some fixed necklace, how many strings you can come up with such that the resulting necklace is the fixed one. So let's look at suppose you have A1, A2 all the way to AK. Then when you wrap it up, you have A1, A2, AK. And similarly, if you have A2, A3, AK, A1, you should have the same thing. And then AK, A1, A2, AK minus 1. So those are given by rotation. And then if you flip this, do reflection, then you should have AK, AK minus 1, A1, and then AK minus 1. A1, AK, A2, A2, A1, AK, A3, AK minus 1, A2, A1, AK. So those are given by reflection of the rotations. Notice that the right hand side, if you wrap that up, you should have AK, AK minus 1, A1. Looks different from the left one, but then if you reflect it, it should give you the same necklace. Okay, as we claimed before, so the cardinality of the set UL just order of the dihedral group. So this is 2K. Okay, therefore, what is the answer? Answer, the different necklace is, the number of different necklace is n times n minus 1 all the way up to n minus k plus 1 divided by 2k. Okay. In particular, you can see the right hand side, the division should be an integer. Although probably you won't have 2k appear directly in the numerator, but the combinatorial interpretation tells you the right hand side must be an integer. Okay, so that is division principle. In reality, you might have many different scenarios to apply different principles, and sometimes you need to combine some of them. So my suggestion is, don't try to remember them, just use the most natural way and get the idea to apply it. So the idea for the last one, the division one, is if you have some symmetry, if you have group action, then you should divide the group action. Okay, also I should remind you that we have a course assistant. So if you he will hold an office hour. So if you have any problems, want to discuss even the homework problems, you can stop by his office hour. I think it's regular. It's a regular time. I will make announcement on Canvas. Okay, next we turn to the K permutations of sets. So definition. Given a set S and integer k greater than 0 and K permutation of S is a sequence A1, A2 all the way to AK, where A1, A2, AK are distinct elements of S. So according to this definition, we already have made some K permutations before. Just think about when you make a string for the necklace, and the string is a K permutation. Okay, and also if K is N, so we will call this N permutation just a permutation. When K equals N equals the cardinality of S. Okay, and let's look at example. Suppose S is a set consisting of ABC 3 elements. Then the permutations of S are ABC, ACB, BAC, BCA, CAB, CBA, and two permutations of S, AB, AC, BC, BA, BC, CB, CA. One permutations of S, A, B, C. Zero permutation of S, empty. So this is a convention we usually make for permutation or combinations. And also no K permutation of S for K greater than 3 in our case. Next, let's look at example 2. Suppose you have set S consisting of integer numbers 1, 2, 3 up to n, and then for K between 0 and n. So what is the number of K permutations of S? Okay, and solution. So for K permutation, actually you have K positions, the first one, the second one, all the way up to the case 1. And each one you are putting some integer numbers, A1, A2, AK. And look at, so we do this order. Step 1, let's look at the first position. Choose the value for A1. So A1 can be any number between 1 to n. Therefore, you have n choices. And then step 2, as soon as, no matter, because our order, we first do the position 1, then after first step, A1 is fixed. No matter what value A1 is, A2 cannot be that value. So A2 should be chosen from 1, 2, 3 to up to n. Get rid of the value of A1. Therefore, no matter what A1 is, A2 have A2 has n minus 1 choices. And similarly, this is just application of the multiplicity principle, but sometimes I would like to forget about the principle, just think about the process. And then for the AK, you can choose from can be chosen from 1 to n and get rid of A1 to AK minus 1. Therefore, you have n minus k plus 1 choices. So totally, you have a product of all these numbers, and we will denote this by KMP. This is a user notation for the left-hand side product, or permutation number, sometimes we also call it. If you still remember, this is exactly the number of different strings for the necklace problem. Okay, next, we introduce some notation which will be very helpful when we do some numerical calculation or some mathematical derivations. So for integer n greater than or equal to 0, define n factorial to be the product starting from n all the way down to 1. Each time you decrease by 1. N times n minus 1 times n minus 2 times 2 times 1. And then here we make some convention. First, if n is 0, then we define it to be 1. And secondly, in this notation, what is KMP? Recall that KMP is n times all the way down to n minus k plus 1. So this is n times n minus 1 all the way down to 1 divided by n minus k times n minus k minus 1 all the way down to 1. So this is n factorial divided by n minus k factorial. And in particular, what is Pnn? Just n factorial. Okay, now let's look at example 3. So at a party, there are 15 men and 20 women. So how many ways are there to form 15 couples consisting of 1 man and 1 woman each? Actually, in your textbook, there are second part for this problem, but that should be done after. That can be done only after we learn what is a combination. So in that problem, we ask how many ways are there to form, for example, 10 couples instead of 15. Okay, so I hope you find the difference between 15 couples and 10 couples. Okay, anyhow, in this problem, since we have 15 couples, that means each man should be in one couple. Okay, then we can decompose the problem or transform the problem into the following one. Suppose you have 15 tables, and each table sitting a man. So first table sitting M1. M1 is a man, and M2 is another man. M15 is 15th man, and then you need to put in woman in each table. So first table, you might put WA1. So W1 to W20, woman. WA2, WA15. Okay, and A1 to A15 are distinct numbers of 1 to 20. Okay, therefore now the real problem is transformed to the following one. How many ways of so what is the number of 15 permutations of the set 1 to 20? And I would still like to do some manually deduction. That A1 can be chosen from 1 to 20, therefore you have 20 choices. A2 can be chosen from 1 to 20, get rid of A1, so you have 19 choices. And all the way down to A15, it can be chosen from 1 to 20, as soon as it's not one of A1, A2 to A14. Notice that A1 to A14 are different, therefore the cardinality of the set is 14. So A15 can be chosen from 6 numbers, can be chosen from a set with cardinality 6. So finally, the total number is a product P2015, or if you would like, you can write as 20 factorial divided by 5 factorial. Okay, now let's look at another example. So given a set S of people, n people, so n is the cardinality of S. So for 1 less than or equal to k, less than or equal to n, seed k people from S around a circular table. And of course, the problem you can guess is how many possible arrangement. But as you can guess, here we still need to identify which 2 arrangements are the same. For example, if the positions matter, then you can just view it as a string instead of a circular table. Okay, and if the seats are different, then it seems like a necklace problem. Okay, but here we have a slightly different version between these 2 extremos. That is, people care about the people who are sitting on their left and the right, but then nothing else. So people care only about who sits left and right to them. And so remark, I would like to use a picture to illustrate the last sentence. So suppose you have people with a red hat and sitting somewhere, and then on his left is a blue-headed man, and then you have a green-headed man, one more left, and then you have purple hat on the last position. And to end that sentence, if these four people are rotate a little bit, just like on the east side sitting the red hat man, and then you have blue hat, green hat, purple hat. The same. So we view this as same. Because for the people with red hair, he always sees the blue one on his left, purple one on his right, and the same thing for all the other people. Okay, but if you do the following, then you have a different situation. So according to the problem, the first one and the third one are different because for example, for the people with red hair, on his left, previously it's people with blue hat, but now it's people with purple hat. So he can tell it's different. People flip it. The neighborhood flipped. Okay. So in some fancy language, that is the symmetry group is rotations, or it's a group of order K or ZK. Sometimes you also use this notation. Okay, recall that previous you have one more generator, you have flip, you have reflection, therefore you have 2K. You double the element, but now you only have K. Okay, so we can solve this problem in the following way. We still first construct strings A1 to AK. We let K people just standing in a line, and then you sit them around the table. So A1, A2, AK, and then you can see here by the similar argument as before, A1, A2, AK is mapped to A1, A2 around table to AK. A2, A3, AK, A1 is also mapped to this configuration. Let's call it configuration. table configuration. And A3, A4, AK, A1, A2, and the last one is AK, A1, A2, AK minus 1. So those different standing positions are mapped to the same table positions. Okay, now by the division principle, it should be the number of different arrangements should be the cardinality of the set of all standings, that is A1, AK are in S, are distinct. And then divided by K. This is because for each table configuration, you can find K pre-images or K standing positions mapped to that. So this, finally, the above one, what is above one? This is P and K. This is a K permutation of n elements. Therefore, P and K divided by K. Okay, and then sum them up, we have the following theorem. So given a finite set S with cardinality n, and for 1 less than k less than n, the number of circular K permutations of S is P and K divided by K equals n factorial K times n minus K factorial. I should make a remark. Don't try to remember it. Remember the group action or how we identify two elements, two K permutations. Or remember the symmetry. Because in different scenarios, you will have different type of questions. Sometimes they view circular K permutations as the same if they are differ only up to some rotation. Sometimes they are viewed same if they can identify by rotation and the reflection at the same time together. So the important thing is remember and or make clear what is the symmetry instead of just remember the number. I guess as soon as you know the idea, you can derive the number very easily. Okay, next, let's look at another example. So, what is number of ways to order the 26 letters of the alpha, beta, so that no two vowels A, E, I, O, U occur consecutively. Solution. So for this real problem, you first you should do is try to transform it into some mathematical problem or some permutation problem. And here we do the following. You have 21 consonants after getting rid of the 5 vowels. Therefore, you have 21 positions. Where you can put in consonants. Okay, also, so let me use box to indicate that. And between boxes, you have circles between them, so that vowels can be put only in the red circles. So those are the position for the circles. Of course, they can left open. So the circles can left open, but the box cannot. Okay, and therefore step 1. Okay, so sorry, I round auto. Run out of the electricity or the pen. So I will say it in words. So for A1, for step 1, you need to compute how many ways you can put in A, E, I, O, U. And for A, you have 22 positions. For E, you have 21 positions. For U, you have 18 positions. So that will be 22 times 21 times 20 times 19 times 18. Okay, then for step 2, you put in consonants. So how many ways are there? You have the number of permutations of 21 elements. So that is 21 factorial. Okay, so totally you have 21 factorial times P 22, 5. Okay, I will stop here. Yeah, hopefully next time I will make this up.